Welcome back. What we're going to be talking about today is a new term, inscribed angles, and we're also going to be talking about a theorem related to inscribed angles. So, first of all, an inscribed angle is an angle that has a vertex on the circle, and the sides of the angle are chords. So here we have angle A is an inscribed angle. We can see that its vertex, wherever I put it, its vertex is on the circle. So that's what makes this an inscribed angle. Remember, let's contrast that to a central angle. In a central angle here, BOC, the vertex is at the center of the circle. So inscribed angle, vertex on the circle, central angle, vertex in the center. What we might be interested in knowing is what is the measure of this inscribed angle. So I have built some calculations in here, and let's take a look. So we can see that the inscribed angle is much smaller than the measure of the inscribed angle is much smaller than the measure of the central angle here, 83 to 83.6, 83.7-ish to 80 to 41.8. So it looks like it's much bigger. What we might want to do is we might want to compare just how much bigger it is. So let's see here. We're going to do a ratio of the angle measures. That's interesting. The central angle BOC and the inscribed angle BAC, the ratio of those angle measures is 2. Maybe I got lucky where I stopped. Let's see. Let's see if we make a smaller angle here. The ratio stays 2, even as the measure of the central angle is changing. And if the central angle gets really big, the ratio stays the same. So we have a theorem, which is that the central angle, BOC, will equal 2 times the inscribed angle, BAC. So I've multiplied both sides here by the inscribed angle, BAC. By the way, I moved the central angle around, but I didn't move the inscribed angle around. So you'll notice that no matter where I put this inscribed angle on the circle, so long as it intersects that same chord BC, we say it intercepts actually, chord BC, then angle A will always be the same because it's in relation to that same central angle. So that's a pretty cool feature of an inscribed angle. It doesn't matter where it is. Even if we go all the way over here, very close to C, it still stays that the inscribed angle is half of the central angle. So there's a corollary here. What if we open this all the way up to 180 degrees for the central angle? So we have this semicircle here on the top. It still holds that the inscribed angle is going to be half of it. So no matter where A is on the bottom semicircle here, these are all 90-degree angles. So that's our corollary. Any angle inscribed in a semicircle is a right angle. So angle A will always be a right angle if it is inscribed in this semicircle down here on the bottom, semicircle BAC. Angle A will always be 90 degrees because it intercepts this top semicircle. So that's it for today. The challenge for you while you're watching at home is to try to prove why this is the case. And I want to give you a little bit of a head start on one case. There's 3 cases you'd actually have to prove here, but I'm going to give you a little head start on one case. Let's imagine that that AC is a diameter. And we know we can just give a value to angle BOC. Let's maybe say it's 50 degrees. There's about 50 degrees right there. If that's 50 degrees and this is a diameter, we can find this angle here. And then let's think about what kind of triangle AOB is. And see if you can prove for yourself why no matter what angle this happened to be 50 this time, but let's make this angle equal to 2x. And let's see if we can prove why angle A would have to be x if the central angle is 2x. The other two cases, once you've proved that, is if the center is inside on the interior of the inscribed angle, and the other version would be if it's not. So you can prove all three of those. The key is to prove this first one with a diameter, and then after that, keep using a diameter in your proofs. So good luck with that, and I'll see you next time. Take care.